Beneath the Bismarck Sea, a profound spatial and scale paradox is currently unfolding. For over 2 months, the planet's most powerful active volcanic eruption has been intensifying completely out of sight, unfolding entirely underwater. On the 8th of May, 2026, at approximately 1:15 Universal Time, seismometers at the Rabaul Volcano Observatory detected the precise signature of magma forcing its way through the crust along a submarine feature known as Titan Ridge. Within hours, an unobserved crisis broke the surface. The observatory identified at least 2 separate active eruption centers on the ridge, positioned roughly 2.5 kilometers apart. This is not a minor seafloor anomaly. It is a massive geophysical event occurring 130 kilometers southeast of Manus Island in Papua New Guinea. Because the entire event is submerged, there are no dramatic surface photographs of a mountain tearing itself apart. Instead, the scale of this crisis is recorded by planetary instruments. Steam and ash plumes climbing between 10,000 and 20,000 feet into the aviation corridors, localized thermal anomalies, and a massive 69-square-kilometer raft of floating pumice rock captured by the European Sentinel-2 satellite, a drifting stone slab with a footprint larger than the island of Manhattan. The environmental deficit is already severe. In early June, these pumice fields drifted northwest, choking the harbors of several islands and systematically destroying the marine life, coral, and seagrass beds that local communities depend on for survival. Yet, as the Rabaul Volcano Observatory, the NASA Earth Observatory, the German Ocean Research Center, GeoMar, and the Smithsonian's Global Volcanism Program track the site, they face an uncomfortable truth. The sheer volume of the ocean leaves scientists mostly guessing at the fine details. The physical strain on the region was confirmed by a strong magnitude 6.4 earthquake striking the central Bismarck Sea, located 191 kilometers southeast of Lorengau, placing it within a critical 30-kilometer radius of the active Titan Ridge eruption. Curiously, just 2 days prior, an independent magnitude 6.4 earthquake struck the South Sandwich Islands region in the far South Atlantic, thousands of kilometers away. While a global chain reaction is statistically improbable, both sites share the exact same structural recipe. They are convergent tectonic boundaries where one slab of the Earth's crust is forced down beneath another, melting as it descends and feeding a hidden line of undersea volcanoes. This weekend of twin subduction zone earthquakes highlights a massive blind spot in global monitoring, pointing directly to a staggering scientific revelation published in July 2026. Researchers repurposed an algorithm originally designed to map impact craters on the surface of Mars and directed it at our own ocean floor. The algorithm identified 73 previously undocumented submarine calderas, the massive bowl-shaped scars left behind by history's most violent volcanic collapses. To put this metric in perspective, prior to this single survey, only 78 submarine calderas had ever been cataloged in the entire history of marine science. A borrowed Martian algorithm instantly doubled the known architecture of Earth's deep-sea volcanic structures, revealing that 68 of these 73 calderas were completely invisible to traditional methods. This points to an almost embarrassing baseline fact. Humanity has mapped the surface of Mars in finer detail than its own seafloor. With estimates of detailed ocean floor mapping ranging from under 5% to a generous 25%, the overwhelming majority of the seafloor remains an unexplored province. This is where the true engine of planetary volcanism resides, winding along a 65,000-kilometer network known as the Mid-Ocean Ridge System, which quietly produces more molten rock annually than all land volcanoes combined. With the discovery of these 73 hidden calderas coinciding with the ongoing Titan Ridge crisis, a fundamental mechanical question emerges. If the planet's primary volcanic engine operates in the one environment we are least equipped to observe, how can we be certain we would even recognize the signs if this entire global system began a coordinated architectural acceleration? To evaluate whether this hidden volcanic network is undergoing a systemic shift, we must analyze the accelerating baseline of modern observations over the past 15 years. The modern instrumental record reveals a sequence of consecutive, record-breaking submarine eruptions, each displacing the last. The timeline begins in 2011 and 2012 with the eruption of Tagoro off the island of El Hierro in the Canaries. This event marked the first time scientists monitored a Canary Island submarine eruption in real time with advanced instrumentation, observing a prolonged disruption of the local marine ecosystem. Immediately following in 2012, the Havre volcano erupted north of New Zealand. Havre produced a massive 400 square kilometer pumice raft, yet because the eruption occurred entirely underwater and far offshore, it completely bypassed human visual detection. The event was discovered only retrospectively when satellite platforms identified the drifting field of volcanic rock. The trend escalated further in 2015, when axial seamount off the coast of Oregon became the first underwater volcano monitored live via a cabled observatory linked directly to the seafloor. By 2018 and 2019, the scale shifted again near the island of Mayotte in the Indian Ocean. An intense seismic swarm culminated in the formation of a brand new submarine mountain rising 820 meters from the seabed, constructed from roughly 5 cubic kilometers of erupted lava. At the time, it was catalogued as the largest submarine eruption ever documented by direct observation, mirroring the intense seismic activity currently recorded around Titan Ridge. This escalating progression culminated in the event of January 15, 2022, when the Hunga Tonga volcano shattered existing models of underwater volcanic capacity. Hunga Tonga demonstrated that the ocean does not merely muffle these systems, it conceals engines capable of fundamentally altering the global atmosphere. The eruption blasted approximately 146 teragrams of water vapor directly into the stratosphere, instantly increasing the total water mass of that atmospheric layer by roughly 10%. The explosion generated an atmospheric pressure wave that circled the globe multiple times, registered on weather instruments across every continent, triggered a Pacific-wide tsunami, and produced hundreds of thousands of volcanic lightning flashes. Crucially, Hunga Tonga was not a historically prominent, heavily monitored system. It was an obscure submarine volcano on a remote volcanic arc, belonging to the exact same classification of structures that the Mars algorithm recently identified by the dozen. The rapid transition of Hunga Tonga from apparent dormancy to a globe-altering event in a matter of hours reveals the critical risk embedded in our marine blind spot. The surrounding seawater acts as a physical muffler, absorbing the micro-earthquakes that typically signal an impending eruption on land. This deviation from traditional geomechanical expectations is further illustrated by the Gakkel Ridge beneath the Arctic Ocean. As the slowest spreading segment of the global mid-ocean ridge system, separating at less than 1 centimeter per year under 4 kilometers of crushing water pressure, classical physics dictated that explosive eruptions were impossible. Yet, researchers investigating a massive earthquake swarm there recovered fresh fragments of pyroclastic glass. The mechanism defying the hydrostatic pressure was pure chemistry. The magma contained dissolved carbon dioxide levels nearly 10 times higher than typical seafloor lava, driving a violent gas expansion that shattered the rock upon ascent. This pattern of hidden scale extends to individual structures like the Tamu Massif in the Northwest Pacific. Covering a surface area comparable to the state of New Mexico or Olympus Mons on Mars, this continental-scale basaltic feature sat unrecognized on our own planet until the 2000s. While modern magnetic data sparks ongoing scientific debate regarding whether it functions as a single central volcano or a stretch of seafloor spreading ridge, its massive scale remains undisputed. The existence of Tamu Massif proves that if the ocean can conceal a volcanic construct of state-sized proportions until the last decade, the presence of 73 undetected calderas is a minor statistical reality. This lack of historical baseline data directly addresses the alternative narratives circulating online, which claim a global volcanic surge is being deliberately hidden from the public. Systems analysis reveals that the data is entirely public, originating from open sources like the NASA Earth Observatory and the United States Geological Survey. The perceived secrecy is not political. It is a physical constraint of the medium. The ocean hides these processes from standard human observation because kilometers of water muffle acoustic and seismic signals. Therefore, science cannot yet definitively state if the global system is accelerating or if humanity is simply developing the machine learning and satellite tools required to observe what has always existed. A record this short cannot definitively rule out a genuine increase in activity, but it confirms that the underwater volcanic engine is far more volatile than old models permitted. The ongoing crisis at Titan Ridge now forces us to confront the immediate future of the Bismarck Sea and the broader mechanics of marine observation. The continuous eruption, active for more than 2 months, presents multiple distinct pathways. The system may persist in injecting vast quantities of pumice into the equatorial currents, maintaining the ecological chokehold on the shallow ecosystems of Manus province. Alternatively, the sustained output of magma could build the structural mass of the ridge sufficiently to breach the ocean's surface, creating a temporary new island, a geological progression previously hinted at by historical eruptive activity in this exact sector during the 1970s. The final possibility is a quiet dissipation of thermal energy, though the recent magnitude 6.4 earthquake suggests that the internal pressures of the magmatic plumbing system remain highly dynamic. Volcanologists are monitoring the site to determine if our current network of remote sensors can even register the exact cessation of such a deeply submerged event. Beyond this localized crisis, the secondary focal point shifts to the evolution of seafloor mapping itself. The July 2026 machine learning survey that identified the 73 undocumented calderas operated at a coarse resolution of approximately 500 meters per pixel. This means the algorithm was only capable of identifying major structural collapses, leaving smaller or more complex volcanic vents completely unclassified. As higher-resolution sonar and bathymetric mapping efforts advance across the remaining unsurveyed swaths of the ocean floor, the data dictates a mathematical certainty: we will discover more volcanic structures. The critical unknown is not the statistical existence of these features, but their operational status. The core scientific objective now is to identify which of these newly mapped calderas possess the volatile chemical profiles and mechanical capacity to execute a sudden atmospheric breaching event like Hunga Tonga. The physical limits of our monitoring systems mean we may not receive the standard seismic warnings that precede subaerial eruptions, as the massive water column continues to damp out low-frequency precursory tremors. This analytical uncertainty underscores the fundamental reality of our current epoch. The largest, most active volcanic system on Earth is the very one we can least observe. The outward signs of activity across Titan Ridge and the global subduction zones are a stark reminder of the planet's underlying energy budget. Whether these synchronized marine events represent a genuine systemic acceleration of Earth's internal heat engine, or simply the first time human technology has achieved the diagnostic sensitivity to witness baseline planetary operations, the analytical conclusion remains identical. We are no longer permitted to view the oceans as static barriers. They are dynamic, poorly understood envelopes concealing massive thermodynamic systems operating under intense pressures. As the ground beneath the Bismarck Sea continues to shift and adjust to these massive magmatic loads, it has effectively forced a reallocation of scientific priority. The tracking of Titan Ridge, the expansion of machine learning crater detection algorithms, and the close scrutiny of deep-sea seismic swarms are no longer isolated academic exercises. They are essential protocols for mapping the structural limits of a hidden global engine that has, through the sheer density of hard physical data, permanently commanded our attention. The structural analysis of this hidden volcanic network requires a final, systematic evaluation of how microscopic physical inputs scale up into macro-level planetary crises. At the base of this thermodynamic chain are the exact chemical and mechanical properties of the magma itself, such as the high concentrations of volatile gases discovered at deep rifts like the Gakkel Ridge. When these dissolved gases, particularly carbon dioxide, exceed standard baseline thresholds by up to 10 times, they alter the viscosity and eruptive mechanics of the magma. The resulting explosive decompression shatters the rock into highly porous, low-density pyroclastic glass and pumice. This microcomponent immediately dictates the nature of the macro-environmental impact observed on the surface. Because the density of this newly formed volcanic rock is less than that of seawater, it rises rapidly through the water column, assembling into massive floating aggregates. As observed via the Sentinel-2 platform during the Titan Ridge event, these structures can span 69 square kilometers, forming drifting basaltic shields that interact directly with ocean currents. The human and ecological consequences of this process follow a strict architectural cascade. Once these massive pumice fields drift into coastal zones, such as the shorelines of Manus province, they shift from open ocean anomalies into mechanical hazards. The floating rock physically blocks sunlight, preventing photosynthesis in vital primary producers like seagrass beds and coral reefs. This sudden light deficit and physical smothering disrupts the entire local marine trophic web, decimating the fish stocks that local populations depend on for dietary and economic stability. Thus, an unobserved chemical shift 4 kilometers beneath the ocean surface directly translates into a concrete socio-economic crisis in coastal communities, demonstrating that these deep-sea systems cannot be decoupled from human geography. This cascade highlights the acute operational limits of modern anthropogenic monitoring. The reliance on a repurposed Martian algorithm operating at a resolution of 500 meters per pixel underscores a profound technological bottleneck. While this methodology successfully doubled the catalog of known submarine calderas by identifying 73 massive structural collapses, it remains completely blind to smaller, highly active volcanic centers that lack the massive footprints of structures like the Tamu Massif. Consequently, the global scientific apparatus is forced to operate under severe informational deficits, managing planetary risks with instruments that are physically limited by the mass, depth, and acoustic damping properties of the global ocean. The twin magnitude 6.4 earthquakes that struck the convergent boundaries of the Bismarck Sea and the South Sandwich Arc within a single 48-hour window serve as a stark reminder of these structural limits. They confirm that the stress fields governing Earth's subduction zones are continuously adjusting to massive magmatic displacements that humanity can barely map. The true engine of global volcanism, the 65,000-kilometer mid-ocean ridge system, runs autonomously beneath the waves, producing the vast majority of the planet's crustal material completely outside the view of subaerial observation networks. Ultimately, the hard data extracted from recent records, from the atmospheric disruption of Hunga Tonga to the persistent outgassing at Titan Ridge, invalidates the conventional view of the ocean floor as a remote, inert boundary. It reveals instead a highly volatile, interconnected thermodynamic matrix operating at the absolute limit of our analytical capacity. Whether the recent cluster of record-breaking events signifies a true mechanical acceleration of the planet's internal heat engine, or merely the initial data points of an advancing observation capability, the systemic reality remains unchanged. The primary volcanic engine of our world operates in the deep ocean, and it has permanently redefined the boundaries of planetary surveillance. The structural investigation into Earth's subaqueous volcanic network culminates in a critical assessment of the absolute limits governing both the natural system and our methods of tracking it. The foundational reality is that the 65,000-kilometer mid-ocean ridge system and its associated subduction zones operate under physical laws that human technology is only beginning to decode. When an underwater event like the Titan Ridge eruption persists for months, or when an explosive anomaly like Hunga Tonga violently adjusts the global stratospheric chemistry by injecting 146 teragrams of water vapor, it exposes the definitive boundaries of our planetary awareness. The primary constraint is not a lack of scientific intent, but the severe physical barriers imposed by the marine environment itself. Seawater effectively dampens seismic energy, scatters acoustic signals, and blocks optical observation, creating an architectural blind spot that covers roughly 70% of the Earth's surface. This inescapable physical limitation completely deconstructs the sensationalized internet myths suggesting a coordinated cover-up of a global volcanic surge. Systems analysis demonstrates that the raw data tracking these deep-sea displacements is entirely transparent and public, captured by open networks like the United States Geological Survey and the NASA Earth Observatory. The widespread perception of secrecy is merely an artifact of human geography. The events feel hidden simply because they transpire under kilometers of crushing ocean water where traditional monitoring frameworks break down. Consequently, humanity remains locked in a state of chronic informational deficit, operating with a baseline observation record that is far too short to definitively confirm whether the global magmatic engine is accelerating or if our diagnostic tools are simply waking up to a permanent baseline level of deep-sea violence. What is certain, however, are the hard structural limits of the systems under examination. The recent deployment of automated algorithms repurposed from Martian crater analysis proved that our catalog of massive submarine calderas was missing more than half of the existing structures, capturing 73 massive scars that were previously invisible. This diagnostic leap confirms that we are dealing with a planetary engine of immense scale that operates largely independent of subaerial observation. The cascading impacts of these hidden systems, extending from deep chemical alterations and high-pressure carbon dioxide outgassing to the macro-scale assembly of 69 square-kilometer pumice rafts that systematically choke coastal ecosystems and devastate local fishing economies, prove that the boundaries between the deep ocean floor and human civilization are non-existent. The crisis at Titan Ridge serves as a sobering final case study. As the system continues to generate strong magnitude 6.4 earthquakes and feed volcanic material into the Bismarck Sea, it acts as an unyielding reminder that the planet's internal heat engine operates on a scale that dwarfs current human surveillance capacity. The smart analytical move is to abandon superficial assumptions of a static ocean floor and accept the real structural boundaries of our monitoring capabilities.